Characteristics of in-phase and out-of-phase modes of vibration. Characteristic of in-phase and out-of-phase mode of vibration. Okay. Two oscillating identical coupled simple pendulum has we know two normal modes of vibration. First is in phase mode. First is in phase mode. In phase mode. Phase mode. And second is out of phase mode. Out of phase mode. Out of phase mode. Okay. Each having its own characteristics. First point, characteristics of in phase mode. Characteristics of in phase mode. In phase mode. Characteristics of in phase mode. Okay. First, the in phase mode can be excited by displacing the bobs of the two pendulums to same side by the same amount and then letting them oscillate purely on their own. Okay. Okay. On their own. Okay. Then the in phase mode can be excited by displacing the in phase mode. The in phase mode can be excited by displacing the box of the two pendulums to the same side by the same side by the same amount and then letting them oscillates purely. Okay. On their own. Second point. The equation of in phase mode is equation double differentiate of x plus omega naught square x equal to 0 and describe the oscillating behavior of the system when it describes the oscillatory behavior of the system when y equal to x minus y equal to 0 or x equal to y. Okay. Third point. The displacement of both the bobs or masses is the same in magnitude as well as in direction, and both the masses continuously oscillate in the same phase. Okay. The displacement of both the bobs, the displacement of both the bobs or masses is the same, or masses is the same in magnitude as well, in magnitude as well as in direction, and both the masses continuously oscillate in the same phase. It means that both the pendulums pass through their mean position or their either. It means that both the pendulum pass through their mean position or through either of the extreme position simultaneously. Okay. The displacement of both the balls or masses is the same in magnitude as well as in the direction, and both the masses continuously oscillate in the same phase. It means both the pendulum pass through their mean position or through either of the extreme positions simultaneously. Fourth point. The amplitude of the two simple pendulums is the same as A. The amplitude of the two simple pendulum is the same is that A. Fifth point. The shape or configuration of the mode is the shape or configuration of the mode is x upon y equal to plus 1. The shape or configuration of the mode is x upon y equal to plus 1. Sixth point. Each pendulum executes simple harmonic oscillation. Each pendulum executes a simple harmonic oscillation at a frequency omega naught equal to under root G by L, which is the natural frequency of free oscillations of either pendulum in isolation, okay? Each pendulum executes a simple harmonic oscillator at frequency omega naught equal to under root upon G by L, which is the natural frequency of free oscillations of either pendulum in isolation. Okay. 7 point. Point 7. In phase mode, there is no effect of the stiffness terms. There is no effect. There is no effect of the stiffness term. Effect of the stiffness term. Stiffness term is of the coupling and the motion. Is of the coupling and the motion coupling and the motion of the two masses, because of the two masses because the spring always has its natural length. It is neither stretched or nor okay compressed. Okay. In phase mode, there is no effect of the stiffness term as of the coupling and the motion of the two masses, because the spring always has its natural length. It is neither stretched nor compressed. Okay. 8 point. Point 8. 8 point. Point 8. A solution of equation first gives capital X equal to x naught cos omega naught t minus phi if the maximum value of x and y be a. If the maximum value of x and y be a, then x not equal to 2a. 2a is the normal mode amplitude. Is the normal mode amplitude. Okay. In phase mode, characteristics of phase and out of phase mode of vibration. Okay. There are two types of vibration of mode. First is in phase mode and second is out of phase mode. Then characteristics of in phase mode. First, the in phase mode can be excited by displacing the box of the two pendulum to the same side by the same amount and then oscillates purely on their own. Okay. Second equation, x double differentiate of x plus omega naught square x equal to 0. It describes the oscillatory behavior of the system when y equal to x minus y equal to 0 and x equal to y. Third point, the displacement of both the balls or masses is the same in magnitude as well as in direction, and both the masses continuously oscillate in the same phase, it means that both the pendulum pass through their mean position or through either of the extreme positions simultaneously. The amplitude of the two simple pendulum is the same is at A. The shape or configuration of the mode is x upon y equal to plus 1. Each pendulum executes simple harmonic oscillator of frequency omega naught equal to under root g by L, which is the natural frequency of the free oscillations of either pendulum in isolation. In the in-phase mode, there is no effect of the stiffness terms as of the coupling and the motion of the two masses because the spring always has its natural length. It is neither straight nor compressed. X equal to x naught cos omega naught t minus pi. If the maximum value of x and y be a, then x not equal to 2a is the normal mode amplitude. Okay. Next, second characteristics of out of phase mode. Characteristics of out of phase mode. Okay. Characteristics of out of phase mode. Okay. So B. Characteristics of out of phase mode. Okay. Characteristics of out of phase mode. Okay. The first point. Okay. The out of phase mode can be excited by the out of phase mode. The out of phase mode can be excited by out of phase mode can be excited by displacing the bobs of the two pendulums, displacing the bobs of the two pendulum in opposite direction by the same amount and then let them oscillate freely on their own. Okay. The out of phase mode can be excited by displacing the bobs of the two pendulum in opposite direction by the same amount and then let them oscillate freely on their own. Second position. The equation of the out of phase mode is double differentiate of y plus omega naught square plus 2s by m into y equal to 0. It describes the oscillatory behavior of the system when x equal to x plus y equal to 0 or x equal to minus y. Okay, this is the equation number second. Okay, third point. The displacement of either mass of either mass bob is equal in magnitude but opposite in direction to the other mass and two masses and the two masses and the two masses continuously oscillate continuously continuously oscillate oscillate continuously oscillate continuously oscillate out of phase by out of phase by continuously oscillate out of phase by an angle of 180 degree, phase by an angle of 180 degree or pi radians are with respect to each other are with respect to each other okay. It means that both it means that both the pendulum pass through the pendulum pass through their mean position in opposite direction are in opposite directions are at their opposite extreme position simultaneously okay. Third point, the displacement of either mass box is equal in magnitude but opposite in direction to the other mass, and the two masses continuously oscillate out of phase by an angle of 180 or pi radians with respect to each other. It means that both the pendulum pass through their mean position in opposite direction are their extreme position simultaneously in opposite direction okay. Fourth point. The amplitude of two simple pendulum is the same. The amplitude of the two simple pendulum is the same. Is that A? Okay. Fifth point. The shape or configuration of the mode is the shape or configuration of the mode is x upon y equal to -1. 6 point. Each pendulum executes simple harmonic oscillator SHO, simple harmonic oscillations at a frequency omega dash equal to under root G by L plus 2S by M equal to under root of omega naught square plus 2S by M. 2s by m. Okay, 7 point. Okay, which is higher than the natural frequency, which is higher than the natural frequency. It is higher than the natural frequency. Frequency of the free oscillations of the free oscillations. Okay, of the free oscillations of either pendulum. Oscillations of either pendulum. Okay, either pendulum. Okay, 7 point. 1 minute. 7.7. In the out of phase mode, in the out of phase mode, the coupling terms as phase mode, the coupling in the out of phase mode, the coupling term S dominates the motion of the two masses, the motion of the two masses, and raise the frequency, raises the frequency of oscillation. It is because the coupling. It is because the coupling spring is either in the stretch. Coupling spring is either in the stretched or in the compressed state. Okay, only once in one time period of oscillations, period of oscillation, the spring acquires its normal length. When the masses pass through their mean position, Okay, 8 point. Our solution of equation second is given by y equal to y naught cos omega dash t minus phi dash. If the maximum value of x and y be a, if the maximum value of x and y be a, then y not equal to 2A is the normal mode amplitude. Is the normal mode amplitude. Okay? Normal mode amplitude. Note. X naught and Y naught. X naught and Y naught are purely mathematical. Are purely mathematical. Are purely mathematical quantities. Mathematical quantities and do not represent the amplitude of the oscillation of either pendulum which has a value a equal to x naught by 2 for the in phase mode and a equal to y naught by 2 for the out of phase mode. Okay. General method of finding normal mode frequency. Okay. Consider a system of two coupled system pendulum of the same length coupled by a spring of stiffness S. Then their equation of motion are. Equation of motion are double differentiate of x plus mg by L into x plus s minus y equal to 0. This is the equation number first, and m double differentiate of y plus mg by L into y minus s minus x minus y. This is x minus y equal to 0. This is the equation number second. Okay, where x and y are the displacement of the bobs two pendulum respectively for their mean positions. Okay, L is the length of each pendulum, m is the mass of each pendulum bobs. I proved is equation number first of previous. Okay, where x and y are the displacement of the bobs, are displacement of the bobs or displacement of the bobs of the two pendulums respectively from their mean position, and L is the length of each pendulum. Length of each pendulum. Okay, length of each pendulum, and m the mass of each pendulum, and m is the mass of each pendulum Okay, I proved that. Okay, now when a coupled system oscillates in a single normal mode, each components of a system vibrates with the frequency of that mode. Therefore, supposing that the system of the coupled pendulum vibrates only in one of its normal mode, let the frequency be omega, then the solution of the show equation are x equal to a cos omega t and y equal to b cos omega t. Why? Now when a coupled system oscillates in a single normal mode, each components of the system vibrate with the frequency of that mode. Therefore, supposing that the system of the coupled pendulum is vibrates only in one of its normal modes, let the frequency be omega, then solution of the above equation are x equal to a cos omega t and y equal to b cos omega t. Okay? And where a and b are the displacement amplitude of x and y at frequency omega, where a and b are the displacement amplitude of x and y at the frequency omega. Okay, double differentiate of x equal to minus a omega square cos omega t and double differentiate of y equal to minus b omega square cos omega t. Okay, substituting a 1 and 2 we have substituting in first and second, substituting first and second, we have first and second we have substituting in equation number first and second we have minus m omega square a plus mg by L into a plus s a minus b cos omega t equal to 0. Okay, and the second minus m omega square b plus mg by L b minus s a minus b cos omega t equal to 0. This is equation number 4 and this is equation number 3. Equation number 3, equation number 4. First normal mode frequency. First normal mode frequency. First normal mode frequency. First normal mode frequency. Iodine 3 and 4. We get a plus b minus m omega square plus mg by L equal to 0. This equation is satisfied when this equation is satisfied. This equation is satisfied when omega square equal to g by L plus 2s by m. This gives second normal mode. This gives the second normal mode. This gives the second normal mode frequency. Normal mode frequency or frequency out of phase mode. Our frequency frequency out of phase mode, okay, out of phase mode as omega equal to under root of G by L plus 2S by M, okay. General method of finding normal mode frequency. Consider a system of two coupled system. Consider a system of two coupled simple pendulum of the same length coupled by a spring of stiffness. Then their equation of motion is m double differentiate of x plus mg by L into x plus s x minus y equal to 0. Equation number 1, m double differentiate of y plus mg by L into y minus s in bracket x minus y equal to 0. Equation number 2, where x and y are displacement of the box, L length of the each pendulum, m mass of each pendulum, and x equal to a cos omega t and y equal to b cos omega t. How to? Now, when a coupled system oscillates in a single normal mode, each component of the system vibrates with the frequency of that mode. They are supposing that the system of the coupled pendulum vibrates only in one its normal mode. Let the frequency be omega. Then the solution of the above equation are x equal to a cos omega t and y equal to b cos omega t. Okay, where a and b are the displacement, amplitude of x and y, and the frequency omega. X equal to minus a omega square cos omega t, and the double differentiate of y equal to minus b omega square cos omega t. Okay. And substituting in equation number 1 and second, we have minus m omega square a plus mg by L a plus s a minus b cos omega t equal to 0. Third, and minus m omega square b plus mg by L b minus s a minus b cos omega t equal to 0. This is equation number 4. First normal mode frequency. Adding second and third and fourth, we get a plus b minus m omega square plus mg by L equal to 0. This equation is satisfied when omega square is equal to g by L plus 2s by m. Okay. Then this gives the second normal mode. Frequency. Frequency out of phase mode, omega equal to root g by L plus 2s by m, okay, in phase mode. Second is phase mode. Okay, phase condition. Substituting omega square equal to g by L, we have a minus b 2s equal to 0, a minus b equal to 0, then a equal to b, which gives the in phase condition, and second out of phase condition. Substituting omega square equal to g by L plus 2s by m in a 5. We have a plus b into 2s equal to 0. Then a plus b equal to 0. Then a equal to minus b, which gives the out of phase or anti-phase condition. Okay. So, next, exchange of energy between two normal modes. Dissimilarities. Frequency of two body coupled oscillators. frequency of two-body coupled oscillator. Okay. Consider two masses M1 and M2 connected by a spring of a stiffness of a force constant S. When the two masses are displaced from their equilibrium position, the spring either contracts or extends depending upon the displacement of the masses. This causes a linear restoring force to be produced in the spring, and both masses being the vibrate harmonically about their equilibrium position. Such system is known as a two-body oscillator or coupled oscillator. A familiar example is a diatomic molecule in which the two atoms are connected by some internal forces known as bond. As no external force acts on the system, the center of mass either remains stationary as move with constant velocity. The motion executed is a simple harmonic. The system will oscillate with frequency under root of h by mu, where mu equal to m1 m2 upon m1 plus m2. Okay. This functions is proof of previous lectures. Okay. And application. What is the application of coupled oscillators? What is the application of coupled oscillator? Okay. Application. Application. First is inductively coupled circuits. Inductively coupled circuits. Inductively coupled circuit. A transformer. Transformer is work as a coupled oscillators. Okay. Inductively coupled circuit. Okay. The two electrical circuits are said to be inductively coupled when the magnetic flux due to current flowing in one circuit threads the second circuit. Okay. And the two circuits are then said to have a mutual inductance according to Faraday's law of electromagnetic induction. Whenever the magnetic flux in one circuit changes, and induced EMF is set up in the other, which is proportional to the time rate of change of a magnetic flux, and last only for the times the change is taking place. Most familiar example is that of a transformer whose working depends on the mutual induction between its primary and secondary coils. Okay? Thanks. Applications. Inductively coupled circuit. Inductively coupled circuit. Okay? Inductively coupled circuit. Two electrical circuit is said to be inductively. Two electrical circuit is said to be inductively coupled when the magnetic flux due to the current flowing in one threads the second circuit. In one threads the second circuit. Okay. Two electrical circuits are said to be inductively coupled when the magnetic flux due to the current flowing in one circuit threads the second circuit. Okay. The two circuits are then said to be have a mutual inductance. According to Faraday's law of electromagnetic induction, whenever the magnetic flux in one circuit changes, an induced EMF is set up. Induced EMF is set up in the other, which is proportional to the time rate of change of magnetic flux, and last only for the time the change is taking place. The most familiar example is that of a transformer whose working depends on the mutual induction between its primary and secondary coils. The power source is connected to the primary. The power source is connected to the primary and secondary is wound over the primary in the same sense. Two inductively coupled electrical circuit are shown. You can show this figure, and let NP represent the number of turns in the primary coils. NP represents the number of turns of the primary coils. If phi is the magnetic flux setup in the primary, flux cannot be flows, only set up in a coil, okay? But current is flowing, okay? Then flux is the magnetic flux setup in the primary when unit current flow through a single turn. When unit current flow through a single turn of the primary coil, then assuming that there is no leakage of flux outside the coil, flux linked with each primary turn NP phi. Flux linked with each primary turn is NP phi. Okay, total flux linked with the primary coil. Total flux linked with primary coil, linked with primary coil is NP and NP phi. Okay, NP and NP phi, that are LP equal to NP square phi. This is the total flux linked with the primary coils. Okay, where LP is the coefficient of self-inductance, where LP is the coefficient LP is the coefficient of self-induction, of the primary, okay? Similarly, if a unit current flowing through a single term of the secondary coil also produces a magnetic flux phi, then flux linked with each secondary term, and the flux linked with each secondary turn. Each secondary turn is NS phi. That is LS equal to NS square phi, where LS is the coefficient of self-induction of the secondary, where LS is the coefficient of self-induction of the secondary, self-induction of the secondary. Okay, if we suppose that all the lines of magnetic flux are due to a unit current in the primary thread, all the turns of the secondary, then total flux lines linking the secondary is total flux lines linking the secondary, okay? Total flux lines linking the secondary is NP phi, okay? NP phi are capital M equal to NP phi equal to under root of LP LS, where capital M is the coefficient of mutual induction between the two coils, where m is the coefficient of mutual induction between the two coils, okay. Coefficient of coupling, coefficient of coupling coefficient of coupling okay. The above result is true only when there is no leakage of magnetic flux. In practice, however, some leakage of flux does take place, and m is the less than under root of LP LS. The ratio capital M upon under root of LP LS equal to K is called the coefficient of coupling. Is called the coefficient of coupling okay. And under root of LP LS is the flux. In practice, however, some leakage of flux does take place, and okay, m equal to under root of LP LS. Okay. Then this is the first application of mutual coupling, okay, of electrical circuit. Okay, and next point, energy transfer between two electrically coupled circuit.